All right, then let's get started. It's my pleasure today to give you a lecture about the Nova Microhypervisor, a research project which initially started at TU Dresden and which now continues to be a project at Intel Labs over here. All right. The next slide you can safely ignore. It's a legal disclaimer from the Intel legal team. Let's move right into virtualization, which is what this research project is all about. Virtualization is quite an old technology. It dates back all the way to the 1970s when Popek and Goldberg defined what a virtual machine is. And they said that a virtual machine is defined to be an efficient, isolated duplicate of a real machine. So the idea is you take an existing physical machine and you virtualize the instruction set, you virtualize all the devices, and you create a virtual machine that behaves identical to a physical machine. It used to work not so well with the x86 instruction set because it contains so-called virtualization holes, instructions that behave differently when you try to run them at a lesser privilege level. And therefore, the instruction set x86 was not virtualizable. Now, there have been different attempts at making the instruction set virtualizable, several different techniques. One is called para-virtualization, where you take the source code, you patch those instructions that are not virtualizable, or another option would be binary translation, where you replace those instructions that are not virtualizable at runtime with traps to the virtualization layer. Or if you don't want to change the source code, then Intel decided to make changes to the x86 architecture and designed a new processor mode of operation called VMX root mode. So the extensions to the architecture are called VTX, Virtualization Technology for x86. And as you can see here on the slide, you have a hypervisor that manages the execution in the virtual machines. And we have two example virtual machines here shown on the left and on the right. So typically, what happens is you enter a virtual machine, you execute instructions, and when something interesting happens inside the virtual machine, something that requires the attention of the virtualization layer, then you take a so-called VM exit, which is a trap to the hypervisor, which gives the hypervisor control of the system. And such a VM exit could, for example, be one of those sensitive instructions, or it could be a device access or an interrupt, something like that. Everything that requires the attention of the hypervisor will cause a VM exit. And of course, the hypervisor has all control over what events cause VM exits and which events don't. And once the hypervisor has gained control, it can, of course, switch to another VM and enter that VM. The event is called the VM entry. And as part of the VM entry, you also have the option to inject interrupts or inject other events. So on the right, the different steps are shown here. For VM entry, you switch from the guest world to the host. For VM exit, you switch from the guest world to the host world. And for the reverse transition, for VM entry, you switch from the host world to the guest world. And they are really two different worlds with all the protection rings. Everything is duplicated. So obviously, the performance of the virtualization environment depends a lot on how fast these transitions are, how fast you can switch between guest and host mode. And there's a structure that manages those transitions, which is called the Virtual Machine Control Structure, the VMCS. And the VMCS holds the guest state for the virtual machine and the host state of the hypervisor. And the VMCS is just a memory page that stores all of those registers and all the state. But you don't write to that page using normal move instructions. Instead, there are two special instructions called VM read, VM write. And the reason for that is that the CPU wants to see all accesses to that page so that it can cache certain registers on die and scratch registers. And as you can see here at the bottom, the transition latencies for the VT, VM entries, and VM exits have decreased quite a lot over the years, from roughly 6,000 processor cycles to 1,000 in 2008. And I think currently we are well below 1,000 closer to the 500 cycle range. So the faster you can switch between guest and host mode, the lower your overhead. So what's the reason for starting a new research project? We looked at existing hypervisors, and those are monolithic in their configuration. Monolithic means that all of the functionality that is required for virtualizing a system, x86 virtualization, storage, network management drivers, all of that is contained in the hypervisor binary, which is typically several million lines of code. I've shown 100,000 here, which I think is doable if you strip everything down. But typically those monolithic hypervisors, Xen, KVM, VMware ESX, Microsoft Hyper-V, there are several million lines of code. And if there's a bug in one of those subsystems, then the whole hypervisor can potentially crash, and every VM that runs on top is exposed to that vulnerability. Also, because you don't have any isolation between the subsystems in the monolithic hypervisor, there are no address-based protections or anything. So in summary, you could say that such a monolithic hypervisor is a single point of failure. So the question is, can we do better than that? Before we talk about an alternative approach, let's first talk about the so-called trusted computing base. What is the trusted computing base? The trusted computing base is defined as the amount of software and hardware that the security of the system depends on. So from a security perspective, it is desirable to minimize the trusted computing base. So make the security depend on as few hardware systems as possible and as few lines of code as possible. And one way to achieve that is to split that monolithic hypervisor code into several smaller components, so enforce fine-grained functional disaggregation. And among those components, enforce the principle of least authority. That means every component only has the minimal amount of rights that are necessary to complete its job, and not any more rights. So, for example, a display driver should not have any possibility to access the disk, or the disk driver should not have any possibility to access the display. And if you design a system according to that approach, you minimize the trusted computing base for all of those components, applications and VMs. So here in the next slides, I've shown a few example hypervisors that are not minimal. For example, Xen and KVM. I'll skip those slides. There's a link to the papers here. You can read the papers yourself. Because we don't have that much time, I'll just skip over those slides. And I'll show you what the security in virtual environments depends on. So as you've probably already understood, the hypervisor is a privileged component, kind of like an OS kernel. So it is a security critical part of the system. Just like an OS kernel, when there's a flaw, a vulnerability in the hypervisor, then the security of all components running on top of it is at risk. And obviously, since the hypervisor is also just a piece of software, it will contain vulnerabilities. So nothing is bug-free. Another point is if you start consolidating multiple physical machines into virtual machines that are now running on a single hypervisor, then you replace physical isolation with logical isolation. And of course, the hypervisor itself, that piece of software, contributes to the trusted computing base. So the overall trusted computing base for stuff running in the virtual machine increases. And furthermore, since the hypervisor is a security critical piece of software, it needs to be configured correctly and it needs to be maintained. So just because the code is bug-free does not mean it is configured correctly. For example, if some administrator configures the memory for two virtual machines to be shared, then obviously one virtual machine could write to the memory of the other VM. And that may not what you want. So loss of isolation between virtual machines has a severe impact because the moment you own the hypervisor, you own every VM running on top of it. And that is quite a scary scenario because it allows you to attack an operating system from behind its back. So if you have a virus scanner or some rootkit detection running in your OS, even in the kernel, then the hypervisor is still sitting underneath that. And there have been all sorts of papers about hypervisor rootkits, how you can attack an OS kernel from below. And the security of a virtual machine does not just depend on the hypervisor it currently runs on, it also depends on all the hypervisors it previously ran on. So if you think, for example, that you might migrate a virtual machine from hypervisor A over the network to hypervisor B, then just because hypervisor B is secure does not mean that the VM has not been corrupted while it ran on hypervisor A previously. So security is a big issue. And vulnerabilities in the hypervisor are real. So I've listed just a few here. There are many more, which show that there are bugs in hypervisor source code that can lead to buffer overflows or to VM escapes, where you take control of the hypervisor from a virtual machine, you break out of the VM. And once you've done that, of course, you own all the VMs. So what can we do? Our approach is to try and secure the virtualization layer by making it as small as possible. And as small as possible means we don't take an existing virtualization layer and strip it down, remove functionality. No, we apply the microkernel construction principle and start from scratch. So we start with a white sheet of paper and think about what do we need to put in and what do we better leave out. And in order to make this hypervisor piece as simple as possible to reduce the complexity, we use hardware virtualization features wherever possible. So VTX, VTD, nested paging are just a few examples of hardware techniques that you can use to make the code in the hypervisor simpler. And of course, as I already said, we don't like this monolithic approach where everything is glued together in one piece of software without isolation between subsystems. Instead, we have one very small privileged component called the microhypervisor, and everything else runs deprivileged at user level. So we have the whole virtualization functionality of the x86 instruction set in the virtual machine monitors that are deprivileged, and device drivers also run at user mode and are deprivileged. And among those different components, we enforce the principle of least privilege. So what does the system look like? Here's a picture that illustrates the architecture. At the bottom, in VMX root mode, which is the host mode, in the green area, we have the microhypervisor, which is roughly 9,000 lines of source code. And it's the only piece in the whole puzzle that runs this privileges, this privilege level 0 in kernel mode. And on top of that, in the red area, we have the OS framework, which runs at user mode. So all of these components run in different address spaces, and they are all separated by different address spaces. So we have device drivers, we have a partition manager, applications, and so forth. The partition manager is kind of like the root task, which initially owns all the resources, and then decides what device driver gets access to what device, what VM gets access to what memory. It kind of distributes the resources to the rest of the system. And on top of that, in guest mode, separated by the thick black line, we have guest mode where multiple different virtual machines run. And inside a virtual machine, you can run an unmodified guest operating system. So no need to patch the source code. You can run the operating system the same way you would on bare metal hardware. And we have, for example, Linux running or Android, all without modifications. And an interesting feat here is that each virtual machine has its own associated virtual machine monitor. So there's no single VMM that manages all of them. Each VM has its own VMM. And the reason for that is if there is a flaw, a vulnerability in the x86 emulation that could potentially lead to a VM escape, then, for example, let's assume that this VMM is broken, then it may allow the Linux VM to escape and to take over that component, but it doesn't affect any of the other components in the system. The hypervisor would continue to preserve the isolation, and also none of the other VMs would be affected. Likewise, if there was a bug in a device driver, then only that driver would crash and render the device unusable, but the rest of the system would continue to run undisturbed. So if you as you can see here, if you sum up the amount of code that is required to run such a system, you would have roughly 35,000 lines of code. The hypervisor, just 9,000, the VMM, roughly 20,000 lines of code, and partition manager and device drivers, 7,000 lines of code. And that is quite a low amount of source code that you would have to trust, or that gets added to your trusted computing base if you wanted to run, for example, Linux in a VM. And another good thing is that all of that code is open source. So there's a download link here at the bottom. The code is hosted at GitHub. So everybody can look at it, find bugs in it, and basically be assured that the code does what we claim it does. So what is the microhypervisor doing? When we constructed the microhypervisor, we thought we would combine virtualization functionality with third generation microkernel functionality. So Nova is based on previous research in L4 and inspired by some other features, for example, from Eros and Pebble. And the goal for the design was to have a high performance, low complexity hypervisor that can host secure applications and VMs. So if we switch back, you can see we can have applications running here. If this, for example, is a banking application, then its trusted computing base would be just the 9,000 lines of the hypervisor to get the isolation from the other components and what little code is required by the application itself. And we also fixed some shortcomings of original L4 kernels, like older kernels did not support multiple processors or had issues with priority inversion during IPC. And as I already said, this started out as a research project at TU Dresden in 2006. And since 2012, the project is now hosted at Intel Labs, and Intel Labs is investing in further development of that microhypervisor. So I've already talked about how we maintain the isolation in the system using different address spaces. But security is not just isolation. It's also the question of how do you distribute access to certain resources in the system. And for that, we use capabilities. A capability could be thought of as a pointer plus access permissions. So it's a reference to a kernel object or a hardware object, for example, a page, coupled with permissions such as read writes, write writes, or in terms of kernel objects, it could be an address space with the right to talk to that address space, or a thread with the right to talk to that thread, and so forth. And there are different types of capabilities. Memory capabilities, they refer to physical memory. I/O port capability distribute rights to I/O ports, and object capabilities are used to configure kernel objects to decide who can talk to whom or who can run on what CPU and so forth. And if you possess such a capability, you can invoke it, you can delegate it to someone else, you can revoke it, or you can translate it. And capabilities are the way to confer rights in the system. So what does a capability look like, or how does this work? In the hypervisor, we have a bunch of kernel objects, and there are 5 different types. A protection domain, for example, would be a container, like an address space or a virtual machine where you can assign resources. An execution context is an activity inside that protection domain. In terms of a virtual machine, that would be a virtual CPU, or if you're talking about an address space, then an execution context would be a thread. We have scheduling contexts that define who can utilize the CPU for how long, at what priority. We have portals that are entry points between different protection domains. So if you want to communicate from one protection domain to another, you would go through a portal. And we have semaphores as synchronization objects. So inside the hypervisor, we have these different objects. And when you create a new object, you obtain the root capability, which is a pointer, as shown here. So this bluish capability points to the protection domain, and the green one points to the execution context. And then when you have created an object and you hold the root capability, you can use that capability to configure the object. Or you can delegate the capability to some other protection domain, and then you have access to the object as well. But the user itself does not deal with the capabilities because they are stored and protected by the hypervisor. The user uses a so-called capability selector, which is just a number. So if the user wanted to refer to that purple capability, it would use capability selector number 3, and then the hypervisor would go, oh, this is 0, this is 1, this is 2, this is 3. So capability number 3 is the one that refers to the scheduling context. And since the hypercall interface uses capability for all operations, the user cannot access objects that it doesn't hold the capability of because it cannot even name those objects. If you don't have a name for it, you can't tell the hypervisor what to do with it. That's why capabilities are so well suited for implementing the principle of least authority. So communication in the system works using capabilities as well. So here we have two protection domains. The orange one is the client protection domain, and the green one is the server protection domain. And the client consists of a thread, an execution context, and this round bubble here is the scheduling context, which allows the client to execute on the CPU. It's kind of like a time slice. On the server side, we have also created an execution context. That one does not have a time slice, so it cannot run because it doesn't have any time. But there's a capability for it, and the server has created two portals, portals A and B, that refer to different services that the server is implementing. Now, if the client wants to talk to the server, it first needs to obtain a capability to one of those portals. In this case, the client has obtained a capability to portal A, which is stored in its capability space. And if the client now wants to call the server, it would issue a hypercall. It would say, call the portal or call the capability number 2, which is 0, 1, 2 is the portal A, and send a message. And the hypervisor would arrange a rendezvous between the client thread going through the portal with the server thread S. And as part of the communication, the hypervisor would donate the scheduling context of the client to the server so that the server now works on behalf of the client, and the CPU time is also, the consumed CPU time of the server is also accounted to the client. And I will talk later about why this is a good idea to implement it that way. And once the server is done, it will reply with the message. There's no need to invoke a portal here because the hypervisor remembers who the caller was. There's a reply capability referring to the client EC. And once you reply to the reply capability, that reply capability will be automatically destructed so that you cannot reply again. So communication is synchronous in that both the client and the server need to be ready and it's CPU local. So they are both on the same core, and that's why the communication is really fast and there are no logs involved. So let's talk about one of the defects that were present in classic microkernels in synchronous IPC. So in L4, for example, you can have a scenario where a client with a scheduling context calls a server, and in L4, servers also have scheduling context. And the client sends a request to the server, and the server now executes on behalf of the client with the client time slice. And that works quite well because the server inherits the priority of the client. It uses the time of the client, but it only works until the whole scenario is preempted. So let's assume that there's a new thread, let's call it X, that preempts the client and the server, the communication, and runs. And after X has gone away again, the classic L4 kernel is unable to recognize that there's a dependency between C and S, and it will no longer schedule the server S on the green scheduling context, but instead will invoke the server S on its own scheduling context. And the effect is priority inversion because the server S now runs with its own priority rather than the priority of its client. And that is quite an ugly problem. And for those of you who are interested in all the details about this, I've put a link to a paper here at the bottom, which describes this effect and all the consequences in more detail. So priority inversion is the problem in shared resource systems where a high priority thread is blocked by a low priority thread. Let's take this example here on the left side. We have a shared resource, and in our case, the shared resource would be a server that multiple clients want to talk to. And let's assume that the green low priority client, so the height on the slide is is referring to the priority. So the low priority green client is first because the medium and the high priority client, they are currently sleeping. So L talks to the server S, and S is now working on behalf of the client L and executing with the priority of client L with low priority. Everything's fine. Now the high priority client H, the blue one, awakens and also wants to talk to the server. But since the server S is currently handling the request of the low priority client, H has to wait. So this is indicated by the dashed line. So H has to wait until the server has responded to L. And so H is now put to sleep and L can execute again. And now we could have a scenario where a medium priority client with a priority higher than L but lower than H awakens and preempts the server. And it's able to do that because obviously its priority is higher than L. So M could now execute forever. L would not continue to run, nor would S, because they have a lower priority. And as a result, the high priority client, which should have precedence over M because of its higher priority, cannot run because it's blocked by S and S is blocked by M. And this is unbounded priority inversion, which is a difficult problem in real-time systems. So you need some sort of mechanism to prevent that. And the solution is priority inheritance. And the way that this works is that the moment that the high priority client wants to talk to the server, the priority of the server is elevated to priority H. So it is higher than M, and M could not run. That's the way it works. So here is the combination of the two mechanisms that the Nova microhypervisor uses. The first one is called donation, which works similar to the classic L4, except that it does not suffer from this priority, from this preemption problem. So when a client talks to the server, it donates its scheduling context to the server and effectively boosts the priority of the server up to that of the client. And another unrelated thread is unable to preempt that scenario. And the other mechanism is helping, and helping deals with the problem I just described, where you have a low priority client that has already donated its scheduling context to the server. So S has been elevated to priority C. And now you need to protect against the medium priority threat here. And that is done because when a high priority client wants to talk to the server as well, the priority of the server is boosted further all the way up to H so that the medium priority client, the orange one, is not able to run. And both of those mechanisms are transitive, so that means they work across multiple IPC links in a call chain. And unbounded priority inversion is not an issue in Nova. So let's talk about how virtualization and communication work together. I already said, when something interesting happens inside a virtual machine, the hardware generates a VM exit, which gives the control to the hypervisor. So in Nova, when you take a VM exit out of the virtual machine, say this Linux VM here, you get control in the hypervisor, and the hypervisor synthesizes a message containing the architectural state of the virtual CPU and sends that message through an event-based portal to the associated virtual machine monitor. And as you remember, there is one virtual machine monitor per VM, so it's clear which VMM this event goes to. And the VMM, the virtual machine monitor, implements all of the complicated x86 emulation stuff. It knows all details about the instruction set, about the devices, all the high complex x86 stuff, which does not reside in the hypervisor. So if the programmer makes a mistake and virtualizes something incorrectly, it will only affect the VMM, and the VMM may crash, but the hypervisor will continue to run. So let's assume that everything works correctly. The VMM resolves the virtual machine event. Could be, for example, a device access that the virtual machine wants to read a block from the virtual disk. In that case, the VMM would have to make another IPC call to the disk driver component. The disk driver would retrieve the block, and then the call chain would be unwinded back all the way to the VMM, and the VMM would respond to that VM exit, and control would flow back into the virtual machine. And since we have this donating call behavior, the whole handling of the event, virtualizing the instruction, reading the block, all of that is done with the CPU time of the virtual CPU. So the virtual CPU pays for that event, which makes sense. Interrupt handling works the other way around. So if there's an interrupt generated in the hardware, the microhypervisor will get control, will signal the interrupt to the respective device driver. So in case of a disk interrupt, it would signal the disk driver. And we do that by using a notifying semaphore. And the disk driver would read the blocks and find out who those blocks go to. For example, if they were for the VMM, it would put them in shared memory and then would notify the VMM also with the semaphore that there was an interrupt. Now the VMM wants to inject that interrupt into the virtual machine. So it first has to interrupt the virtual machine. There's a special hypercall called recall, which causes the virtual CPU to come back from the VM and visit the VMM. And then once the virtual CPU has visited the VMM, we can piggyback the virtual interrupt back and inject it into the VM. That's the control flow of interrupt injection. Another interesting aspect is memory management, because unlike a traditional OS kernel, which just has a page table per address space, Nova actually has 3 different page tables per protection domain. The first one is the host page table, which defines the layout of an host application. So depending on whether we are talking about the 32-bit version or the 64-bit version, it will be a 2 or 4 level page table, allowing you to address 3 gigabytes or 128 terabytes. And the hypervisor is part of the upper portion of that address space, kind of like a traditional OS kernel. So this host page table is used for all applications and everything running at user mode on top of the hypervisor. Device drivers, applications, the VMM, the root partition manager, the GUI, everything uses the host page table. For virtual machines, there's another page table set called the nested page table, which defines the address space layout in guest mode, in VMX non-root mode. And that is the 4-level page table defining the physical memory layout of the virtual machine. So each virtual machine gets a guest physical address space that is 0-based. So it starts at address 0 for the guest, but in the host, it may result in a totally different memory area. So for example, for a Linux guest that has 2 gigabytes of guest physical memory, so the guest sees addresses 0 to 2 gigabytes, but in host physical memory, it may actually be a region from, say, 8 gigabytes to 10 gigabytes. So the nested page table performs that translation. And the IOMMU uses yet another page table called the DMA page table, which is up to 6 levels deep. And that page table controls where DMA transfers from devices go in the physical memory system. So how does memory virtualization work? We actually have 2 page tables that we need to consider here. One is the page table created by the guest. So we have a 4-level page table here for, say, a 64-bit guest. It's pointed to by control register CR3, which is the root of the page table tree, and then we have 4 levels. And normally you would translate a linear address using or through those 4 page tables, and you get a physical address out of it. Now with virtualization, the problem is different because you have the host page table, the nested page table as well. And the nested page table translates guest physical to host physical addresses. So the translation step is twofold. We first translate a guest linear address through the guest page table into a guest physical address. And then we translate the guest physical address through the nested page table into a host physical address. And unfortunately, we need to do that for every step. So in CR3, there's a guest physical address. So where the guest thinks its page tables are, we need to translate that address through the host page table, through the nested page table to a host physical address. Then we know where the PML, the page middle level is. And again, in that page table, we find a guest physical address that we need to translate all the way through the host page tables or through the nested page tables to find the PDPTE. And then we do that for the other level as well. So as you can see, quite a lot to do for the MMU. Nested paging increases the page walk from the previous 1, 2, 3, 4 accesses to 24. So these translations are added to the page walk. Obviously, you don't have to do that every time because we have a TLB which caches previous translations. So if we have a TLB hit, then the access will be really fast. But if you miss in the TLB, then you have to do all this page walking to translate from a guest linear to a guest physical and then to a host physical address. If you don't have an MMU which is able to do this two-level translation, then the hypervisor needs to implement a trick called a virtual TLB. So here again, you see the translation step, guest linear address, is translated through the guest page table under the control of the virtual machine kernel to a guest physical address. And the guest physical address is then translated by the nested page table in the hypervisor to a host physical address. So the MMU needs to comprehend the two-step translation process. Older processors don't implement support for the two-level translation. So what the hypervisor needs to do instead is it needs to manually do this end-to-end translation and fold the guest page table and the nested page table together into a so-called shadow page table. So the shadow page table is basically the concatenation of these two translation functions and is managed also by the hypervisor. And the MMU would then use the shadow page table. And the behavior is kind of similar to a TLB. That's why it's called a virtual TLB, because the shadow page table performs the same end-to-end translation as the TLB. Needless to say that whenever something changes in the nested page table or something changes in the guest page table, you need to make the same changes in the shadow page table. And typically that means you need to flush the shadow page table because the translations might be invalid. That's why virtual TLB is quite a bit slower than using the MMU for that. But if you don't have support in the MMU, then you need to use the VTLB. So let's talk a bit about device drivers. Device drivers have been found to be the most prominent source of bugs in operating systems. 90% or more of crashes in Windows are not due to the Windows core kernel, but are due to device drivers. So it makes perfect sense to move the device drivers out of the kernel and implement them as regular user-level applications. So we move the device drivers out of the kernel, run them as regular apps, and this has certain implications. Because, for example, we now need to allow user applications to do DMA. And DMA, direct memory access, typically uses physical addresses, and user applications don't know physical addresses. So that's a problem. And I'll tell you the solution in the next slide. Another interesting approach is that you don't want to give a virtual machine only virtual devices. Sometimes, for performance reasons, you may want to give a virtual machine access to a hardware device, for example, a network card. And if you do that, then you bypass the virtualization layer for all of the network traffic events, and you can achieve much higher data transfer rates because you don't have to emulate the device in software, and you have much greatly reduced amount of VM exits. And again, for such a directly assigned device, you need to control the use of DMA, because if a device is able to program an arbitrary physical address into its if the driver is able to program an arbitrary physical address into its DMA, then it could DMA into another VM, or it could DMA into the hypervisor and overwrite code, and that's something you don't want. So what can we do against that? There's a technology called VTD, Intel Virtualization Technology for Direct I/O, and it's sometimes referred to as IO-MMU. And the behavior of an IO-MMU is similar to that of an MMU in the processor, except that it doesn't sit in the processor, it sits somewhere in the chipset. Or if you don't have a chipset, as in modern cores, it sits somewhere in the root complex of the PCI hierarchy. And the IO-MMU uses also a set of page tables to translate DMA addresses to host physical addresses. And the way that this works is as follows. A normal DMA transfer consists of this tuple shown here at the top left corner. It consists of the requester ID, the bus, device, and function of the device. It consists of the DMA target address, which used to be a physical address, but let's now call it a DMA address, and it consists of a length. And this request is sent over the interconnect to the memory controller, And in between sits the DMA remapping engine or IOMMU. And it uses the bus device function of the request to index into a so-called context table to find a device descriptor. And for each device, this device descriptor can configure, this context can configure a set of page tables that are used to translate the request. For example, for device 1, the bluish translation structures would be used. And then the IOMMU takes the address of the request and translates the address through those translation structures to get a host physical address. And that way, you can translate addresses programmed by the guest or by a user-level device driver to host physical addresses. And if you don't want to allow access to a particular region, then you make an invalid translation for that. So you don't put a page table entry into the translation structures. And again, there's a so-called IOTLB, a context cache and a translation cache in the IOMMU that caches recent translations, so you don't have to do that for every memory access. So the IOMMU is useful for two things. First, you can translate DMA addresses from guest physical to host physical or from host linear to host physical. And you can also use the IOMMU to protect regions. So you would never put a hypervisor physical address into one of those translation structures. And if there was no translation that ever went to a hypervisor page, obviously nobody could DMA into the hypervisor. So now that you've understood all of the hardware features that are present and the architecture of Nova, let's look at what the attack surface in Nova is and what would happen if you were to attack Nova from different angles. So first, let's talk about what happens if you perform an attack from inside a guest OS. And it doesn't matter whether we are talking about an attack from a user-level application or from an OS kernel, because we treat the whole virtual machine as a black box. So the only thing in the hypervisor that you could attack is the message passing interface that sends the state from the virtual machine through the hypervisor to the VMM, because that's the only path that is exercised when a virtual machine has a pending VM exit event. And if you find a flaw in that, and the code is roughly, say, 250 lines of code or so, then you could attack the hypervisor. But that path is well exercised and easily cross-checked, so it's very unlikely. It's more likely that you would find a bug in the virtual machine monitor, and you might be able to crash or take over the VMM if you find such a bug. So what happens if you own the VMM, the user-level virtual machine monitor? Well, then the attack surface increases a bit. It's not just the message passing interface, it's now the whole hypercall interface. So you can now issue all sorts of hypercalls, you can try to create objects, you can try to map resources around. But the damage you can do is limited because you only have access to those components for which you hold capabilities. So if the capability setup is such that you cannot, for example, talk to a device driver, then yeah, you cannot interfere with the operation of the device driver, even if you own the VMM. Or if you don't have access to the GUI, well, then you cannot output anything. So even attacks from the VMM are not all that dangerous because the VMM is just an ordinary user application from the point of view of the hypervisor. Let's assume that you actually manage to compromise the device driver. So maybe there's a buffer overflow in your network driver and somebody has managed to take over the network driver over the network through an exploit or so. Then the question is, what can you do from inside that device driver? And yeah, you can only do what the capability setup allows you to do. You can DMA to those regions of memory that your driver is allowed to do DMA to. And remember, the IOMMU restricts what regions you can perform accesses to. And you can never attack the hypervisor from a device driver because the hypervisor regions never show up in any of those page tables. Nobody ever DMAs into the hypervisor. So also the amount of damage you can do from a device driver is quite limited. Now the question is, if you have such a system with all of those components, then you have quite a bit of isolation and robustness is quite improved because a crash or a flaw in one component only affects the availability of the function implemented by that component, but not the integrity or the confidentiality of any other component. But of course, there's a price associated with that, because now that the system consists of so many different components, you have to communicate from one component to another. And there's overhead associated with that, because whenever you send a message from one component to another, you have to perform an address-based switch. And an address-based switch is potentially costly because you have to change the page tables, you may have to flush the TOB, and so forth. So the performance of the whole system will depend a lot on the efficiency of the microhypervisor, which performs all the context switching. And there we really pulled a few tricks in Nova. And one of those is that Nova does not implement a process-style execution model like traditional kernels, where you have one kernel stack per thread. Instead, Nova implements an interrupt-style execution model, where you just have one kernel stack per core. And the way that this works is, if you look at the graph here at the bottom, then you could think that this green box is a kernel entry point, and the green dot here to the right is a kernel exit point. And depending on what hypercall you issued and what function you wanted to call, there are multiple different paths through the hypervisor. So one hypercall might take this path, and another hypercall might take this path. And what Nova does is it chooses the path according to the hypervisor parameters, or the hypercall parameters. You enter the hypervisor here, you call the red function, you call the blue function, you call the orange function, and then the stack frames for those functions, they pile up on your kernel stack, just like in an ordinary kernel. But then when you get preempted in the kernel, or you block, you get put to sleep, then we don't maintain the content of that kernel stack anymore, but we discard it. We fold the whole result of that path, the whole result of the computation is folded into the continuation parameters. So you store that in this red control block, and you store a pointer to that function in which you will continue after your preemption is resuming. So this continuation stores a pointer to the point where you will resume, together with the result of the path that you've already taken. And then if you implement it that way, you can throw away your kernel stack, because none of that stuff is relevant anymore. You're just interested in the result. And then when the thread is activated again, you will resume at the orange dot, and you will just finish with the remainder of your execution path, and you will exit to user mode. So in some sense, this is a lot of goto programming. You never go back in the kernel. You only go in one direction through the kernel. You jump from one function to another, and you never return. And doing it that way basically cuts the execution path already in half, because a normal kernel would then go all the way back out here, and it would unwind the stack frames, and none of that is required in Nova. So obviously, this has a few implications, because you cannot preempt the execution inside the kernel at arbitrary points, because, as I said, when you get preempted, you lose your kernel stack. So you can only preempt inside the hypervisor if you are able to express the result of your computation in a clean and ideally in a minimal way. So let's assume that this is your execution path, and here at that point in your execution path, there's an interrupt that would preempt you. So a normal kernel would switch away from the thread right here and activate another thread. What we do instead is we enter the interrupt handler, we set a hazard that says, oh yeah, at some point in the near future, we should switch away from that thread, but we can't do it right now because we don't know what is going on here in that execution path. We might be in the middle of updating a linked list, or we might be holding a bunch of logs, and you can't just throw away your kernel stack when you're holding logs. So we will just flag this event. We set a hazard, and then we will return to the execution path and continue with whatever we were doing up to the nearest preemption point. And this preemption point is a point in a code path where we can say, oh yeah, here we have computed an intermediary result. We don't hold any logs. We are in a clean state, so we are not in the middle of updating some data structure. So we can safely discard the kernel stack and configure a preemption. And then we switch away here at this preemption point, and then another thread runs. Now you may argue that this limits the preemptibility of the kernel to some amount, so there's no fine-grained preemption in the kernel, and that is true. However, you don't need to be artificially preemptible anywhere, because the processor recognizes interrupts only on instruction boundaries. So you will never take an interrupt in the middle of an instruction, only between two instructions. So if you take two instructions and you ask what is the length of those instructions, then you have the minimal length of a preemption. So for example, take an IO port access that can easily take 3000 cycles to complete, just an in or an out instruction. So it makes no sense to be more than 3000 cycles preemptible inside the kernel, because an IO instructions would take just as long. So you can space your preemption points as far apart as the longest instruction that a normal user could call, without limiting your worst case execution time. So this kind of kernel stack design has certain performance implications. If you have a single kernel stack design, you have reduced cache and TLB footprint. So just a single stack for all of the threads, no stack per thread. So the overall resource usage is reduced. Also your cache footprint. Because you never unwind the kernel stack, you never do a return instruction, you basically discard it. You don't need to ever restore the registers that are saved on the kernel stack. You also don't have a misaligned return stack. And you can go back to the user mode anywhere on your kernel stack. Also, I talked to you about preemption points. If you have a code pass in the hypervisor that is so short that it's, say, much less than 3000 cycles, then you don't need to enable interrupts at all. You can just rush through the kernel from one user mode application to another user mode application. And if that takes less than, say, 3000 cycles, then you don't need to enable interrupts in the hypervisor at all. And as I already talked to you about those hazards that encode certain specific events, like a pending preemption, they are much more than just this one hazard. For example, there are also hazards for managing read, copy, update quiescent states, or managing the information that the FPU is active. So hazards are an efficient means to encode special conditions in the hypervisor that occurred during an execution pass and that need to be handled before you return to user mode. So all of those tricks obviously show in the performance. If you look at IPC performance, inter-process communication, then this is dominated by three important factors. The first is the cost for entering and exiting the kernel, indicated by the blue box. So the blue box is the overhead for performing a sysenter, an STI instruction to enable interrupts again, and a sysexit to exit back from the kernel. And as you can see, for all different kernels, that's the same number, because that is a hardware cost. So 158 cycles is the sum of sysenter, sysexit, and STI instruction on an Intel Core i7 with 2.6 gigahertz. The second part of the cost is the overhead of the kernel execution path. So the instructions that are executed in the kernel during a process, during an inter-process communication. Switching the page tables, saving the registers, copying the message from one thread to another, and so forth. And as you can see here, Nova is quite a bit faster than the L4 Fiasco kernel or the L4KA Pistachio kernel. And that is the old Fiasco kernel. The newer one with capabilities will be a lot slower. And the sum of the blue and the red box would be the cost for transferring a message from one protection domain, from one thread to another thread in the same protection domain. So in this case, it's 278 cycles for a round trip IPC between two threads in the same address space. So less than a last level cache miss. If you communicate from one thread to another thread in a different address space, then the hypervisor also needs to change the page tables and flush the TLB. And this is where the green box comes into play. This is the overhead for the TLB, flushing the TLB, repopulating the TLB after an address space switch. And that is the biggest factor. And as you can see here, the larger your working set is, the more TLB misses you will have, not just in the user application, also in the hypervisor. And again, here, the sum of all three is the cost for performing a round-trip IPC between two threads in different address spaces. And Nova is here 23% faster than the old fast-pass IPC in L4. And for communication in the same address space, Nova is even 33% faster. Obviously, the overhead of the TLB depends on how many pages you access. So here at the bottom, you see the communication overhead in cycles for communicating between two threads in the same address space. And on the x-axis, you see the number of memory pages that have been accessed. So for 0 pages, it would be roughly 278 cycles, as I already showed you. And then for each additional page, you pay 4 or so cycles more. And that is the number of cycles for an L1 cache hit. The red curve here shows the impact of TLB misses when you perform IPC between threads in different address spaces, other PD. Then you see the more pages you access, the more TLB misses you have, and the cost increases quite a bit. And the blue one is using a processor feature called VPIDs, Virtual Process Identifiers, where you have TLB tags in the TLB so that you don't have to flush the TLB during an address space switch. So as you can see, that is just as fast as the communication in the same PD. It has the same slope. There's just an offset here, and that is the offset for flushing the TLB for the address space switch. These 300 cycles in both directions, and then you don't have the TLB refill cost. So the curve is just as steep as the green one. So if you have a processor with tagged TLBs, then the TLB refills will go away. So let's look at the overhead of the virtualization layer. Here we have compared the performance of Nova to other virtual machines. For example, Linux-based KVM, VMware ESXi, the Zen hypervisor, or Microsoft Hyper-V. And the benchmark was a Linux kernel compile that we ran in a virtual machine with a single virtual CPU and a virtual disk and 512 megabytes of guest memory. And as you can see here, Nova is less than 1% slower than if you were executing that benchmark on a bare metal machine with the same configuration. All of the other virtual machine monitors or hypervisors are at least twice as slow, or they have an overhead of 2 to 4%. And what's even more interesting is if you look at the blue box. The blue box is the overhead that you have when you just enable this nested paging. So that's the overhead caused by the MMU due to the two-step translation process. If you subtract that from the red box in Nova, you will see that the overhead of the hypervisor is even smaller. So 0.5% overhead is caused by the MMU, and another 0.3 is caused by the virtualization in the hypervisor, in the VMM, and the communication. And if you are interested in more details, there's a paper here that we published at the Eurosys conference in 2010, which describes all of the things in more detail. So putting this in perspective, here we have a diagram that shows at the x-axis the TCB size, the size of the trusted computing base lines of code. So Nova is roughly in 30,000 if you add all the components up. And Hyper-V is at least 1 million, probably even more. And on the y-axis, you have the performance overhead for a Linux kernel compiler. And as you can see here, the closer you are to origin, the better you are. And Nova excels actually in both. It's both small and a lot faster than the other hypervisors. So this busts the myth that microkernel-based systems are slower. If you design them right, if you use all the performance features of the CPU, you can both be smaller and more secure, and you can be faster than monolithic systems. And the faster is actually a result of the smaller footprint. It's not so much that we are better coders. It's more that a smaller kernel has a much smaller hardware footprint. So what's the status? Currently, the hypervisor is able to run on x86 machines. Doesn't matter if it's an Intel machine or an AMD machine. It runs on 32 and 64-bit machines. It supports nested paging, symmetric multiprocessing, and the IOMU. So last week we ran Nova on a 64 core machine with 128 gigabytes of memory also. Quite a bunch of virtual machine that just worked. It also works with different user level environments. So there are actually three. There's the Nova userland, the old user environment. There's the Nova runtime environment. And there is the G-Node framework that I believe you will hear something about later today. The user level virtual machine monitor implements a bunch of different device models. So models for the NIC, for SATA, graphics, PCI. And it's able to also assign platform devices directly to the guest. That works just out of the box. So unfortunately, there's no 64-bit support in the VMM yet. So that means currently you are limited to 32-bit operating systems in the guest. But once somebody implements 64-bit support in the VMM, you will also be able to run 64-bit guests. The hypervisor can already do that. Yeah, so in summary, I hope you've enjoyed this presentation and you've learned that a disaggregated virtualization layer makes quite a lot of sense because it implements additional isolation boundaries, which improve the security. I hope I could show you that the performance of such a system can be excellent if you use the right hardware features. And I also need to say that Nova is just a research prototype. So we haven't implemented, any production system also out of it. It's an open source project, so everybody can participate in it, download it, use it, find bugs in it, contribute to it, whatever. We've reduced the size of the trusted computing base by at least an order of magnitude, in some cases even two, compared to monolithic systems such as Zen or Hyper-V. And at the same time, we've exceeded the performance of those systems. So that's quite an interesting achievement. So with that, I'm at the end of my presentation and I can take questions if you have any.